This video is about the rates of change of polar functions. This is AP Precalculus topic 3.15. If you appreciate the content, please give it a like. In this section, we will learn ways that we can describe characteristics of the graph of a polar function. Given a polar function r equals f of theta, we know that r represents the signed radius of the function. We use the phrase signed radius because r can be positive or negative value. As we trace the graph of a polar function, we are interested in whether the graph of r equals f of theta is getting closer to the origin or further from the origin over a given interval. If r is positive and increasing, the distance between r and the origin is increasing. If r is negative and decreasing, again, the distance between r and the origin is increasing. If r is positive and decreasing, the distance between r and the origin is decreasing. If r is negative and increasing, again, the distance between r and the origin is decreasing. Example 1. The graph of f of x equals 1 plus 2 sine x is shown below on the interval from 0 to 2 pi. Use the graph below to complete the given table with the appropriate intervals. Where is f positive and increasing? I've highlighted in blue the part of f of x that is positive because it's above the x-axis. I've highlighted in orange the parts of f that are increasing. See how f is rising from here to here and from here to here. So f is positive and increasing on the interval from 0 to pi over 2, union the interval from 11 pi over 6 to 2 pi. The blue part of the graph still shows where f is positive. The orange part now shows where f is decreasing. See how f is falling from here to here? We can see that f is positive and decreasing from pi over 2 to 7 pi over 6. The blue part of the graph is where f of x is negative. See how this is the part below the x-axis? The orange part of the graph shows where f of x is increasing. See how it's rising from here to here and from here to here. We can see that f is negative and increasing only from 3 pi over 2 to 11 pi over 6. The blue part of the graph still shows where f is negative, but now the orange part shows where f is decreasing. See how it's falling from here to here? We can see that f is negative and decreasing only from 7 pi over 6 to 3 pi over 2. Earlier in the video, I told you that if r is positive and increasing, the distance from the origin is increasing. You can see that easily on a rectangular graph such as this one, where the x-axis represents the pole. Notice that on the interval from a to b, f, which equals the r value, is positive and increasing. You can easily see that the r value is in fact getting further away from the pole. Let's look at that same interval on the polar graph. We are talking about the interval from 0 to pi over 2. As we rotate from theta equals 0 to pi over 2, we are tracing out this portion of the graph from A to B. And you can again see that the r value is getting further away from the pole. On the interval from B to C, f is positive and decreasing. Notice that the value of r is getting closer to the pole. Let's compare this to the same interval on the polar graph, from pi over 2 to 7 pi over 6. That is from here to here on the polar graph, from B to C. And again, notice that the r value is getting closer and closer to the pole on this interval. On the interval from C to D, f is negative and decreasing. Can you also see that the r value is getting further away from the pole? Let's compare this portion of the graph to the interval from 7 pi over 6 to 3 pi over 2 on the polar graph. However, because the r values are negative, the graph is going to appear in the opposite direction. So, from 7 pi over 6 to 3 pi over 2, we are actually graphing this portion of the graph from here to here. Notice again that the distance from the pole is increasing on this interval. The point of this exercise is to reinforce your intuition that what you see happening on the rectangular graph will match what happens on the polar graph. I'm going to put C here again on the rectangular graph because it's actually a loop and C is here at the pole and we're going away to D and then back to C again. So it makes sense that C will appear twice on this graph. On the interval from D to C, F is negative but increasing. Notice that on this interval the distance between F and the pole is decreasing. Let's compare what's happening on the rectangular graph from D to C to what's happening on the polar graph between 3 pi over 2 and 11 pi over 6. Since we have negative r values, we are talking about the part of the graph in the opposite direction. So we are going from D to C like this. And again, notice that the distance between r and the pole is decreasing. Let's look at this last interval from 11 pi over 6 to 2 pi, which will take us from C back to A on the polar graph. On the rectangular graph, we can see that F is positive and increasing. Notice that the distance between F and the pole is increasing on this interval. On the polar graph, from 11 pi over 6 to 2 pi, we are traveling from C to A. Notice again how the r value is increasing on this interval. You can trust that whatever you see happening on the rectangular graph will match what's going to happen on the polar graph. AP exam tip: it is often helpful to sketch the graph of the given function in rectangular coordinates when attempting to describe the behavior of a polar function. Example 2. Consider the graph of the polar function r equals f of theta, where f of theta is equal to 2 minus 4 cosine theta in the polar coordinate system on the interval from 0 to 2 pi. Which of the following statements is true about the distance between the point with polar coordinates f of theta comma theta and the origin? Let's make a rectangular graph for f of theta. Moving the 2 to the end, it's a bit easier to see that this is the d value, which gives us the midline. The 4 in the front, I'm ignoring the negative sign for a moment, tells us that the amplitude is 4. So it will be 4 up and 4 down from the midline. The negative sign gives us a reflection over the x-axis, so this will be an upside down cosine function. So it's going to be looking something like this. To determine the intervals where f is positive and negative, we need to know the x-intercepts. So let's set f of x equal to 0 and solve. Subtracting 2 from both sides gives negative 4 cosine theta is equal to negative 2. Dividing both sides by negative 4 gives cosine theta is equal to positive 1/2. If you have not yet memorized these 9 trig facts, pause the video and memorize the chart right now. Better late than never, I guess. We can find the reference angle by asking the cosine of what angle is equal to 1/2. We have memorized that the cosine of pi over 3 is 1/2, so the reference angle is pi over 3. On the interval from 0 to 2 pi, here are the 4 angles with a reference angle of pi over 3. Since we want cosine to equal positive 1/2, we will stick to quadrants 1 and 4, where the x value and thus the cosine is positive. The angle in the first quadrant with a reference angle of pi over 3 is pi over 3 itself, So that's one solution and one x-intercept. We can think of 2 pi as 6 pi over 3. So this angle in the fourth quadrant is 5 pi over 3. That is another solution and the other x-intercept that we were looking for. So right here is 5 pi over 3. Option A says the distance from the origin is increasing on the interval from pi to 5 pi over 3. Well, the distance from the origin is decreasing on the interval from pi to 5 pi over 3, not increasing. So the answer is definitely not A. Option B says the distance from the origin is increasing on the interval from 5 pi over 3 to 2 pi. Remember that on a rectangular graph, the x-axis represents the origin or the pole. So we can see that on the interval from 5 pi over 3 to 2 pi, the point is getting further away from the pole. In other words, the distance between the point and the origin is increasing. This matches the statement for option B. Let's just make sure that the justification is also correct, because f of theta is negative and increasing on the interval. Let's see. F of theta is negative and not increasing. F of theta is negative and decreasing on the interval. So close, but the answer is not B. This makes me want to pause and check to see how many of these we could have eliminated without actually even looking at a graph. We know that when these words sort of sound the same, the distance from the origin is increasing. So positive and increasing. Do you hear how those sort of sound the same? So this part of option A made sense. If f is positive and increasing, the distance from the origin is increasing, just not on this particular interval. But if f is negative and increasing, the distance would be decreasing, not increasing. Do you hear how these have a different vibe? Negative, increasing. They sound different. The distance from the origin would be decreasing. So we knew this could not be the answer even before looking at the graph. If f is positive and decreasing, the distance from the origin will be decreasing. When these sound different, the distance is decreasing, and that is what we see in the statement for option C. So C is still a possibility. If f is negative and decreasing, the distance from the origin will be increasing. When these sort of sound the same, the distance should be increasing, not decreasing, so we know D is not going to be the answer without even looking at the graph. So we know C is going to be the correct answer, but let's check our answer by looking at the graph on the interval from pi to 5 pi over 3. From pi to 5 pi over 3, the distance from the origin is in fact decreasing, just like it says in part C, because f is positive and decreasing on this interval, which also matches the justification. So the answer is C. Example 3. The graph of f of x equals 3 sine 2x on the interval from 0 to 3 pi over 2 is shown in the rectangular coordinate system. If the polar function r equals f of theta, where f of theta is equal to 3 sine 2 theta, is graphed in the polar coordinate system on the interval from 0 to 3 pi over 2, on which of the following intervals is the distance between the point with polar coordinates f of theta comma theta and the origin decreasing? Option A says the interval from 0 to pi over 4, so that would be from here to here. The distance from the origin, which is represented by the x-axis, is increasing. We are looking for where the distance between the point and the origin is decreasing, so the answer is not A. Option B speaks of the interval between pi over 2 and 3 pi over 4. So let me start this over. From pi over 2 to 3 pi over 4 is this interval right here. The distance between the origin, which is represented by the x-axis, and the point is increasing on this interval. All right, we are getting further away from the origin. We are looking for a decreasing distance, so the answer is not B. Option C speaks of the interval between 3 pi over 4 and pi. That's going to be from here to here. Notice that we are getting closer to the origin. The distance between the point and the origin is decreasing. So the answer is C. But let's follow through and see why D is not the answer. Let's talk about relative extrema and polar functions. Another characteristic that arises when we study polar functions are relative extrema, minima, and maxima. For polar functions, if r equals f of theta changes from increasing to decreasing, or from decreasing to increasing, then the function has a relative extremum on the interval corresponding to a point that is relatively closest or farthest from the origin. Example 4. Consider the graph of the polar function r equals f of theta, where f of theta is equal to 1 minus 2 sine 2 theta in the polar coordinate system on the interval from 0 to pi. Which of the following statements is true about the graph of r equals f of theta? Let's make a rectangular graph for f of theta. I am moving this one that's in the front to the end, so you can more easily see that this d value is the new midline. There's been a vertical translation. So this is the midline right here. The 2 in the front, I'm ignoring the negative for a second, tells us that the amplitude is 2. So 2 above and 2 below the midline. So the highest value will be here and the lowest value will be here. The negative sign indicates a reflection over the x-axis, so this will be an upside down sine function. Let's put some numbers on the horizontal axis. The b value of 2 tells us the period. The period for a sine function is always 2 pi divided by the b value, so in this case that's 2 pi divided by 2. The 2's cancel out and we get that the period is pi. That's why we're going to put pi here at the end. Then half of pi is pi over 2. And then half of that is pi over 4. And then this is 1 pi over 4, 2 pi over 4, and 3 pi over 4. The answer choices mention pi over 3 and 2 pi over 3. So I feel like we should get those values on our graph. Here's 0, pi over 4, pi over 2, 3 pi over 4, and pi shown on the unit circle. Pi over 3 is a bit bigger than pi over 4, so it'll be right here between pi over 4 and pi over 2. Similarly, 2 pi over 3 will be between 3 pi over 4 and pi over 2. Before we even look at the graph, let's eliminate any of these answers that don't even make sense. We know that r equals f of theta will have a relative extremum, meaning a relative max or a relative min on an interval, if r changes from increasing to decreasing or from decreasing to increasing. Specifically, if r changes from increasing to decreasing, then r has a relative max on that interval. On the other hand, if r goes from decreasing to increasing, then r has a relative minimum on that interval. Option A says that r equals f of theta has a relative minimum on the interval because r equals f of theta changes from negative to positive. Well, that's not correct. Changing from negative to positive does not mean that r has a relative minimum. We are looking for r to change from decreasing to increasing. That's what gives you a relative minimum. So the answer is not going to be A no matter what. Option B says R has a relative minimum on the interval because R changes from decreasing to increasing. That is what we are looking for, so B is a possibility. Option C says R has a relative maximum on the interval because R changes from positive to negative. Again, changing from positive to negative is not relevant to the existence of a relative maximum. For a relative maximum, we want R to be changing from increasing to decreasing, not positive to negative, so C will not be the answer. Option D says R has a relative maximum on the interval because R changes from increasing to decreasing. That makes sense because if R changes from increasing to decreasing, we do know that R has a relative maximum on that interval, so D is a possibility. We've narrowed it down to either B or D. Both options B and D refer to the interval from 2 pi over 3 to pi. So let's just look over at the graph and see if R is going from increasing to decreasing or from decreasing to increasing on that interval. So the interval from 2 pi over 3 to pi is from here to here. So notice that on this interval, R does go from increasing to decreasing. So we can see that R has a relative maximum on this interval. And actually, we know that that relative max will occur when theta is equal to 3 pi over 4, because that's when R is at its maximum value of 3. So the answer is D. The graph of R equals f of theta has a relative maximum on the interval from 2 pi over 3 to pi because R equals f of theta changes from increasing to decreasing. Way back in topic 1.2, we learned that the average rate of change of f on the interval from A to B is given by f of B minus f of A over B minus A. This will be no different for the polar function R equals f of theta. Geometrically, the average rate of change indicates the rate at which the radius is changing per radian. Example 5. Consider the graph of the polar function R equals f of theta, where f of theta is equal to 3 minus 3 cosine theta in the polar coordinate system. What is the average rate of change of R equals f of theta on the interval from pi over 2 to pi? First, we must show the setup. The average rate of change of f on the interval from pi over 2 to pi will be given by f at pi minus f at pi over 2 divided by pi minus pi over 2. Substituting pi for theta, f at pi is equal to 3 minus 3 cosine pi. Pi is right here, and cosine is the x value on the unit circle. The x value right here is negative 1. We have 3 minus 3 times negative 1. Negative 3 times negative 1 is positive 3. So this is 3 plus 3, which equals 6. So f at pi is equal to 6. Similarly, f at pi over 2 is equal to 3 minus 3 cosine of pi over 2. Pi over 2 is right here. Cosine is the x value, which is 0. So we get 3 minus 3 times 0. 3 minus 0 is 3, so f at pi over 2 is 3. Substituting these values back into our expression for the average rate of change, f of pi was 6, so we have 6 minus f at pi over 2, which is 3. Hopefully you intuitively know that pi minus half of pi is pi over 2. If you need to, you can make like denominators by multiplying by 2 over 2. So we have 2 pi over 2 minus 1 pi over 2, which is pi over 2. Obviously, 6 minus 3 is 3. And when you divide by a fraction, you multiply by the reciprocal. So we have 3 times 2 over pi. This gives us a final answer of 6 over pi Kabam! Example 6. The figure shows the graph of the polar function r equals f of theta, where f of theta is equal to 3 sine 2 theta on the interval from 0 to 2 pi in the polar coordinate system. On which of the following intervals is the average rate of change of f equal to 0? On the interval from a to b, the average rate of change of f is given by f of b minus f of a over b minus a. The question becomes, under what circumstances will this average rate of change equal 0? In previous courses, we learned that a fraction will only equal 0 when the numerator is equal to 0. So the average rate of change will equal 0 when f of b minus f of a is equal to 0. Well, that means, adding f of a to both sides, the average rate of change will equal 0 only when f at b is equal to f at a. It makes sense that the average rate of change would equal 0 because we are talking about an interval over which there was no change in the value of f. We are looking for the interval where f of b is equal to f of a. For example, option A will be the answer only if f at 3 pi over 4 is equal to f at pi over 4. Substituting 3 pi over 4 in for theta, we have 3 sine 2 times 3 pi over 4. This is 6 pi over 4, which simplifies down to 3 pi over 2. So we have 3 sine of 3 pi over 2. 3 pi over 2 is right here on the unit circle. Sine is the y value on the unit circle, which is negative 1 right here. So this is 3 times negative 1, which is negative 3. Similarly, substituting pi over 4 in for theta gives 3 sine 2 times pi over 4. 2 pi over 4 simplifies to pi over 2. So this is 3 sine pi over 2. Pi over 2 is right here on the unit circle. Sine is the y value. The y value is positive 1. So this is 3 times positive 1, which is equal to 3. F at 3 pi over 4 is not equal to f at pi over 4. So the average rate of change will not be 0. A is not the answer. F at 3 pi over 4 turned out to be negative 3, and f at pi over 4 turned out to be positive 3. Let's find f at 5 pi over 4 and 7 pi over 4. F at 5 pi over 4 is 3 times the sine of 2 times 5 pi over 4. That's 10 pi over 4, which reduces to 5 pi over 2. We can think of pi as 2 pi over 2, and we can think of 2 pi as 4 pi over 2. So 5 pi over 2 is going to be right here. And sine is the y value on the unit circle, and the y value right here is positive 1. So we have 3 times 1, which equals 3. So now we know that f at 5 pi over 4 is 3. What about f at 7 pi over 4? That's 3 sine 2 times 7 pi over 4, which is 14 pi over 4, which reduces to 7 pi over 2. Let's see, what is the sine of 7 pi over 2? Let's locate that point on the unit circle. If we go all the way around and back, that's 2 pi, and we can think of that as 4 pi over 2. If we go around again, that's going to be double that, which is 8 pi over 2. So 8 pi over 2 is this position right here. So 7 pi over 2 would be pi over 2 before that. So 7 pi over 2 is right here at the bottom of the circle. Sine is the y value, and the y value right here is negative 1. So we have 3 times negative 1, which is negative 3. So we have just found that f at 7 pi over 4 is equal to negative 3. The average rate of change will be 0 on any interval where f of b and f of a are the same. So for example, from pi over 4 to 5 pi over 4, the average rate of change would be 0. Or between these two, from 3 pi over 4 to 7 pi over 4, the average rate of change would be 0 because f at b and f at a are equal. Let's just look at each option one at a time. From 3 pi over 4 to 5 pi over 4, nope, those are not the same. From 3 pi over 4 to 7 pi over 4, that's from here to here, those are the same. The answer is C. And just glancing at D, from pi over 4 to 7 pi over 4, that's from here to here. These are not the same, so D is not the answer. Another fun way to solve this problem is to sketch a rectangular graph for f of theta. Because of the b value of 2, we know the period will be 2 pi divided by 2, which is simply pi. So that's why I'm going to count out 4 quarters of a period, 1, 2, 3, 4, and I'm going to call it pi. So pi is right there. That means halfway is going to be pi over 2. This will be pi over 4. Now I'm going to do multiples of this. So this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4 is 3 pi over 2, 7 pi over 4, and 8 pi over 4 is 2 pi. The 3 in the front tells us that the amplitude is 3. So 3 above 0 and 3 below. We have memorized that one period of the sine function looks like this. And here's a second period for you. On a rectangular graph, it's much easier to see where the output values are the same, compared with a polar graph, where at each one of these 4 points, we are at a distance of 3 from the pole. However, at a glance, we cannot tell if we are talking about an r value of positive 3 or negative 3. But on the rectangular graph, we can see that from pi over 4 to 5 pi over 4, there is no change in output value. It's positive 3 and positive 3. From 3 pi over 4 to 7 pi over 4, the average rate of change will be 0. The output value in both cases is negative 3. In other words, on a rectangular graph, the average rate of change is the slope of the line. So if we are looking for an interval on which the average rate of change is equal to 0, we simply identify an interval on which the slope is 0. So this is another way to know that on the interval from 3 pi over 4 to 7 pi over 4, the average rate of change is 0. The slope is 0 on a rectangular graph, so the answer is C. By contrast, if we look at one of these intervals which is incorrect, like for example pi over 4 to 7 pi over 4, at a glance you can tell that the slope is not 0, the average rate of change will not be 0. Example 7. In the polar coordinate system, the graph of polar function r equals f of theta is shown with a domain of all real values of theta on the interval from 0 to 2 pi. On this interval of theta, the graph has no holes, passes through each point exactly one time, and as theta increases, the graph passes through the labeled points A, B, C, and D in that order. On which of the following intervals is the average rate of change of r with respect to theta the least? According to the setup, we need to hit points A, B, C, and D in order as theta increases. So as we rotate, I want you to keep track of whether the value of r is increasing, decreasing, or staying the same. Because if the value of r is increasing, on that interval the average rate of change of r is positive. If r is decreasing, the rate of change is negative. And on an interval for which the r value stays the same, the rate of change is 0. On the interval from A to B, the value of r is going from 3 to 3. So the r value is the same on this interval, which tells us that the rate of change of r is 0. Now consider the interval from b to c. Can you see that the r value is increasing on this interval? It's actually going from 3 to 5. But what matters is that the value of r is increasing, so the rate of change of r on this interval will be positive. What about the interval from c to d? Can you see that the r value on this interval is not changing? The r value here is 5, and the r value here is also 5. Since the r value did not change, the average rate of change on this interval is 0. And finally, on the interval from d to a, we can see that the r value is decreasing on this interval. Therefore, the rate of change of r on this interval will be negative. We were looking for the interval on which the average rate of change of r with respect to theta is the least. A negative average rate of change is definitely less than a positive average rate of change and less than 0. So D is the answer. In previous units, we learned how to use the average rate of change to estimate the value of a function. Our strategy was to write the equation of a line in point-slope form and then use that linear equation to estimate the value. We love to use point-slope form because all we need is a point and the slope. For the point, we can use any known input-output pair of the function, and for the slope, we use the average rate of change on the given interval. Example 8. The table above gives values of the polar function r equals f of theta at selected values of theta. Use the average rate of change of r equals f of theta on the interval from pi over 6 to 7 pi over 6 to approximate f at 5 pi over 6. To write the linear equation which we will use to estimate this value, we are going to need a point and the slope. For the point, we can use any known input-output pair. Let's use the input-output pair pi over 6, 2. Notice I'm treating this like rectangular coordinates. I'm not doing r, theta. For the slope, we will need to calculate the average rate of change of f on this interval. The average rate of change of a function on the interval from a to b is given by f at b minus f at a divided by b minus a. F at 7 pi over 6 is negative 1, and f at pi over 6 is 2. So we have negative 1 minus 2 in the numerator. In the denominator, we have 7 pi over 6 minus 1 pi over 6, which is 6 pi over 6. Negative 1 minus 2 is negative 3, and 6 pi over 6 reduces down to simply pi. So the average rate of change on this interval is negative 3 over pi. And that is the slope that we will use to write the linear equation, negative 3 over pi. For the point-slope form of a linear equation, we usually write y minus y1 is equal to the slope times x minus x1. However, the input variable is theta, so I'm going to call it theta minus theta1 instead. Now we can write the linear equation that we will use to approximate the value of f at 5 pi over 6. It'll be y minus y, so in this case y minus 2, is equal to the slope, which is the average rate of change, negative 3 over pi, times theta minus theta, so theta minus pi over 6. In order to use this linear equation to approximate f at 5 pi over 6, let's get y by itself by adding 2 to both sides. So we have y is equal to negative 3 over pi times theta minus pi over 6 plus 2. To approximate f at 5 pi over 6, we simply need to evaluate y at 5 pi over 6. So we are going to substitute 5 pi over 6 in for theta right here. So we have negative 3 over pi times 5 pi over 6 minus pi over 6, and then plus 2. So let's see, y at 5 pi over 6 is equal to negative 3 over pi times 5 pi over 6 minus 1 pi over 6 is 4 pi over 6, which reduces to 2 pi over 3. And then the plus 2. Notice that these pi's will cancel each other out. So y at 5 pi over 6 is going to equal negative 6 over 3 plus 2. Interesting, because negative 6 over 3 is simply negative 2. So y at 5 pi over 6 is equal to negative 2 plus 2, which of course is equal to 0. In other words, f at 5 pi over 6 is approximately equal to 0. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.